for 3 consecutive 4-digit numbers, natural numbers which are divisible by prime squared. I remember natural numbers are just positive integers. Now let's do 2-digit numbers. I know an example for that. 2 squared divides, you guys seen this vertical bar, divides 48. 4 times 12 is equal to 48. And of course, the next, whoops, that's a 48. And also 7 squared clearly divides 49 since it's equal to 49. Notice these are consecutive so far. And you guessed it, 5 squared divides 50. Since 2 times 25 is equal to 50, right? So this would meet the condition of the problem, okay? This would meet the condition of the problem, but notice these are just 2-digit numbers. We're looking for 4-digit numbers. Now, I only know how to work this, and I just winged this. I just kept trying until I got it, on this one, okay? This is an example for 2-digit numbers, but we're looking for 4-digit here. And it turns out I read this problem in a number theory textbook where they were dealing with the Chinese remainder theorem, and so I wouldn't have known how to do it. But here's the obvious way of doing it with the Chinese remainder theorem. Get this system of equations where the moduli are co-prime pairwise, relatively prime pairwise. 2 squared is a prime, square of a prime, 3 squared, and they're relatively prime, which is a condition for the remainder theorem to have a nice constructible solution. Okay? Now, notice what I did here, I didn't want to try to write out, I would make a mistake if I did this, but the Chinese remainder theorem, we call it the CRT, not cathode ray tube, but Chinese remainder theorem. All right, and so this is a statement from I think from Van den Eyden's number theory textbook, Charles Van den Eyden. Okay, a fine number theory book, but this is a statement of the Chinese remainder theorem. Now notice, for us to fit, the moduli here are subscripted values of k. And so you would have to write this one right here as n congruent to -1, right? And we're just trying to make it fit this form here. So n congruent to -1 mod 3 squared, and then n congruent to -2 mod 5 squared. And notice it's not even important to know that 5 squared is 25 or 3 squared is 9. It's better to leave it in the prime form. Okay, now, so here we go. Now, y'all, I've done most of this already. Again, you can see where the 0, here's n congruent to 0, right? N congruent to -1, n congruent to -2. And so I won't spend too much time on this other than finding the multiplicative inverses. But you see 0, -1, and -2 are exactly this 0, this -1, this -2. As far as the K1s go, okay? You see, notice that you have the K sub I here as part of the constructible solution. Now, of course, this will be in our context, right? This will be in our context. Okay, n is equal to this letter. That's just the letter they chose to use when they wrote this textbook, okay? And notice this is kind of bad language, but there's 3, they're using n for the upper bound of the upper limit of the index. But anyway, let's not get confused by the letters. There's certainly x sub 1, x sub 2, and x sub 3. And this x sub 1 is the multiplicative inverse of the product of the moduli divided by the index of whatever moduli you're on, okay? And so that's what all of that, I've tried to write out what it is without ever knowing that this is equal to 900. This is equal to 900, but it's not useful to really know that for this problem, okay? The numerators are 900, right? You would have 400, or 100 times 9 is 900. Not important to know, though. All right, so I did as much work as I could right here. Notice I left the 0 part out, and this -1 you see here is this -1, this -2 is this -2. And all I'm going to do is just show you how I found the arithmetic inverse. Mind you, we're looking for 4-digit numbers. So -8, the way I found -8 was just to write down 100. Okay, 100, let me just make sure I got room here. 100 times x sub 2. Okay, you see, y'all, I'm looking directly at this object right here to find my x sub 2. We've already, 0 was this one, so it got wiped out, right? And so we're going to do 100 x sub 2 congruent to 1 mod 3 squared, and that's 9. Okay, and you see that's exactly this statement right here. Okay, now it turns out that that's a pretty easy thing to compute directly. The other one wasn't. I'm not going to mess with it, but you would get that x sub 2, and you can, by inspection, you can see that x sub 2 has to equal to, or can equal to 1, right? Equal, not congruent, but equal. See, because if you put a 1 right here, you get 100 minus 1 is 99, which is clearly divisible by 3 squared. Okay, we had to say that's 9, right? Now, but you see, 1 is not going to get us a 4-digit number, so I tried -8. Notice that this is congruent. And you could have done that directly just by, I guess, but this is the way I did it. Okay, so this -8 right here and this -8 are the same thing. And in a similar fashion, you can find -9 as the arithmetic inverse for x. X sub 3 will be -9. And you can carry on in a similar way. It's a little more of a battle computationally. All right. Anyway, when you do that, you get this number 1448, but notice this is equal to n. Okay. And so we are interested in consecutive numbers. So it would be, remember, we're dealing with n plus 1, n plus 2. And so our 4 consecutive numbers are 1448. And what's going on with these 4-digit numbers? Each of them is divisible by a prime squared. So 1449. And I bet you guys can tell which squared prime is going to do the next one here, 1450, right? These are the answers. Not saying they're the only answers, but they are 4-digit numbers. And the Chinese remainder theorem has helped us to establish that these 3 consecutive numbers are divisible. This one would have to be divisible by 2 squared, right? Easily, I think. This one, I'm not sure what it's divisible by. Have no idea. But 25 definitely divides this one, right? 25 divides that, and 25 is 5 squared, right? So I don't know what it is for this, but you can compute it if you want to. These are the answers right here: 1448, 1449, and 1450 are 4 consecutive 4-digit numbers, each of which is divisible by some prime number squared. This would be 5 squared. This would be 2 squared. I'm not sure. It looks like it might be 3. Does this pass the divisibility test? No, for 3. 13, 7. Yeah, it does. Look, I bet you it's 3 squared, because notice this passes the divisibility test for 3. 9 plus 4 is 13, plus 4 is 17, and 18. So the sum of the digits is divisible by 3. That means the number is divisible by 3, since 10 to the n is congruent to 1 mod 3. So that's it, folks. These are, and y'all, if you think this is a trivial problem, try to find 3 consecutive 4-digit numbers that have a squared prime divisor, just randomly doing it. Okay, it's not easy, and I guarantee you the first 3 you pick, if you're just kind of winging it, it won't work. It won't be right. Okay, so the Chinese remainder theorem was a big help here, and also I got this by winging it because 2 digits aren't as hard. I literally sat around at Starbucks for about 35 minutes and figured out this is the first time it happened. I don't know if it's the first time or not, actually. There may be some smaller ones where this is true. I'm not certain. But I do know this is true. 2 squared, 7 squared for 2-digit numbers. But doing it, winging it for 4-digit numbers is much more of a challenge. And you may stumble upon the correct answer. But this was the Chinese remainder theorem to me has always been interesting. But I don't ever really remember it. I don't use it enough. But this is a nice formulation of it, which we used to produce the solution we were seeking. So this is the answer: 1448, 1449, 1450 have that property. Thank you for viewing.